So these are few numericals that we will be going over. I would be solving the first two, and the third one and may be taken as a practice problem, and there are few other practice problems as well. So let's start with the first one. It is a 3-meter long tube which is 1.4 centimeter in diameters, is subjected to a uniform heat flux. So it is a problem of uniform heat flux of 2.2 exponent 3 watts per square meter. It contains this fluid, ethylene glycol. So we need to find out the properties of ethylene glycol at a flow rate of this much. So that is Q, because it has the units of cubic meter per second. So it is volume flow rate and not the mass flow rate. So we can convert volume flow rate into mass flow rate very easily. The liquid enters the tube at a bulk temperature of 20 degrees Celsius. So that would be TBI, or what you call TMI. In our book they represent this mean temperature as TM, whereas in some texts they write that bulk temperature as TB. So the fluid, when the fluid enters the tube, it is at a mean temperature of 20 degrees Celsius. Determine the fluid outlet temperature. So we have to find out the temperature of the fluid at pipe exit. So it would be Tm naught. This is the unknown, and the tube wall temperature at outlet. So wall temperature at outlet, we may call it Tw naught or we may call it Ts naught. Since it is a uniform heat flux problem, so therefore Ts will not remain constant from location to location, rather it will vary. So we are given this heat flux over here. So we can find out total Q by multiplying that heat flux by the area. So we get so many watts. Further, mass flow rate can be found out, because while calculating the things we usually require mass flow rate and not the volume flow rates. And if you recall, we had also come across the mass flow rate in one of the expressions of Reynolds number as well. So mass flow rate can then be found out using the product of the continuity equation, product of density, area and velocity. So A and V can then be written as Q, where Q is the volume flow rate. So Q is equal to AV. So we will get the mass flow rate as 0.0035 kilograms per second. Now we have to find out Tm naught, right? So Tm naught only appears in the expression of Q is equal to mCp delta T. Right? So we will be starting with mCp delta T, where m would in fact be mass flow rate. Only then Q would then be in watts. So Cp of ethylene glycol would be a known quantity, because we will be finding out all the properties from the table, just like we used to find out the properties of the fluids in previous chapters problems. TMI is provided and Q is known. So using this equation we will be able to find out the value of Tm naught. But there is a little hitch, which is that the properties would be evaluated at this temperature, at the mean of the mean temperature at inlet and exit, means Tmi plus Tm naught over 2. So we do not have Tm naught. In fact, that is the temperature that we need to find out. So at this point of time, in order to find out the properties, at least Cp, we must assume Tm naught. Now the assumption, as we have seen in previous problems, must be a good approximation. It should not be just an assumption out of nowhere. Rather, we should try our best to make it a good approximation. Now, taking a look at other parameters, the TMI is 20 degrees Celsius. So, of course, we will not, and the heat flux is 2.2 kilowatts per square meter. So, the temperature of ethylene glycol should increase over a length of 3 meters. So at least we should not assume any value less than 20 degrees Celsius. We may assume 40, 50, 60, 80, right? So I have assumed over here a value of 60 degrees Celsius. That is fine. So you may assume it as 40, or someone may assume it as 80. Having a deviation of 10 or 20 would not would only bring in a change of half of that difference in the mean temperature, half of the difference in the calculation of the mean temperature. Therefore, the evaluation of the properties will not vary by a large amount. So, I mean, this is the way forward. So, by putting in the values of Q and mass flow rate and Cp, so we will get an average temperature of 313 Kelvin, and from the same table that we have been using before to find out the properties of the fluids, we can then determine the value of Cp by interpolating. So we will get at last the value of Tm naught as 52.7 degrees Celsius. So it is close to 60, right? Someone could have assumed it as 40, so even then it would have been good enough. So I mean, this is the way forward. This is how we move forward to solve the problem. Then we will adjust T bar. T bar as per this new value of Tm naught will be about 310 Kelvin instead of 313 Kelvin, right? So since we take the average of the temperature, so that deviation from the actual value between that actual value and the assumed value will not really make a very large difference unless we assume a value which is either very small or either very high, right? Now, so this is how we will find out Tm naught. The second thing that we need to find out over here is the surface temperature. Is the surface temperature at the exit. So surface temperature will be found out using HA delta T. Right? So we will use this expression of Newton's law of cooling, where we will write Q as H times A times Ts minus T infinity. In fact, it would not be T infinity and it would not be Ts either. So since we have to find out the temperature of the wall at outlet, so you can write it as Ts naught or Tw naught, that is the same thing. And since we are trying to work out the temperature at the outlet, so therefore the mean temperature or the bulk temperature will be the one corresponding to outlet. So therefore it would be Tm naught and it will not be Tmi. Now if we are to find out Ts naught or Tw naught from this expression, we must know the rest of the parameters. So we already know Q. Area is a known quantity. Tm naught has already been found out, so the only unknown is H. So now the problem is the same as the problems of chapter number 7. So we have to somehow find out H, and of course H would be found out with the help of one of the expressions of Nusselt number. And Nusselt number, since the expressions of Nusselt number involve the use of Reynolds number and Prandtl number, and it also depends upon the type of the flow, its selection. So therefore we would be finding out the Reynolds number and Prandtl number and viscosity. So therefore Reynolds number would now be written as Um and not U infinity times diameter over viscosity. So we do not have the velocity, we have the dia, and the viscosity can be found out because from that table where we have found out the Cp from. So if we use this simple expression of Q is equal to AV, we would be able to determine the velocity. It will be 0.021 meters per second. That would be the mean velocity. Now the mean velocity would then be kept in the expression of Reynolds number, and we get this value as 30.6. So since it is less than 2300, the flow would be considered as laminar. Now we will check whether the flow is fully developed or not, because if the flow is fully developed, then there is no expression of Nusselt number, rather there are values of Nusselt number. Whereas if the flow is not in the fully developed region, it is in the entrance region, then there are expressions of Nusselt number that we must use. So in order to find out whether it is fully developed or not, we will find out the hydrodynamic entry lengths. Hydrodynamic entry length and thermal entry length, these two entry lengths. So for laminar flow, as discussed previously at the start of this chapter, hydrodynamic entry length is given as 0.05 Reynolds number times diameter, and if this is multiplied by Prandtl number, we get the thermal entry length. So by putting in the values, we get it as 0.021 meters. It means that from the start of the pipe till 0.021 meters, so this would be the length that it will take, that the flow will take, so as to get a uniform velocity profile. Now what is the length of the pipe? The length of the pipe is given to us as 3 meters, right? So this length 0.02 meters is less than 3 meters. It means that for some initial portion of the pipe, the flow would be under the entrance region, and after this 0.021 meter length, after this length, it will become hydrodynamically developed. Similarly, the thermal entry length, fully developed length, would be 2.2 meters. Again, this is less than 3 meters. So for 2.2 meters, that length would be considered as entrance length for temperatures. Whereas after 2.2, it would be considered as fully developed. It means that the flow is fully developed at outlet, both hydrodynamically and thermally. So since it is a case where we are given that the heat flux is constant, so we need to refer to that particular case where the Nusselt number would be, I will take you to that particular slide. So if the flow is laminar, and if the flow is fully developed, and if it is the constant heat flux case, then Nusselt number would be 4.36. So therefore we will consider it as 4.36. So therefore this would be considered as 4.36. I mean, the Nusselt number would be taken as 4.36. And if when it is equated to HD by K, again K would be found out using the same table, and we need to find out three properties all the time: nu, K, and Prandtl number. So we will get H as 79, and if we then put it in that particular equation, if we put this H in this particular equation, so we will get the outlet temperature at the surface as 80.4 degrees Celsius. So the temperature of the wall would vary, and at the outlet its temperature would be 80.4 degrees Celsius, and also the temperature of the fluid will also vary. At inlet its value is 20 degrees Celsius, whereas while it is flowing through the pipe, it is getting heated up. So since it is getting heated up, so at the end its temperature will raise from 20 degrees Celsius to 57.4 degrees Celsius. So that would be the end of the first problem. Now moving on to the next problem. It says air. So it is no more ethylene glycol. It is air now. Air at 2 exponent minus 4 kilograms per second. So that would be the mass flow rate of air, and 27 degrees Celsius. So that would be the value of T infinity. That would be the value of T infinity, 27 degrees Celsius. It enters a rectangular duct. So as soon as it enters a rectangular duct, we will consider this as the bulk temperature at inlet, and the duct is rectangular, so it is no more a circular duct. That duct is 1 meter long, and 4 millimeter by 16 millimeter on a site. So it is 1 meter long and it is 4 millimeter by 16 mm on a site. So its cross section area would be 64 square millimeters. A uniform heat flux of 600 watt per square meter is imposed on the duct surface. So it is a problem of uniform heat flux case. What is the temperature of the air and the duct surface at the outlet? So temperature of air at the outlet means Tm at outlet, not outside, rather at outlet, at exit. And similarly we have to find out the duct surface at exit. So it would be Ts at exit, or we may call it as Ts naught. So we have to find those things out. So again, in order to find out Tm naught, we would be using the same expression. Right? It would be mCp times Tm naught minus Tmi. This is one expression, and if the parameters are known, we can also use this one, but we will see if what data is provided to us. So now, first of all, if we make use of Q is equal to mass flow times Cp times Tm naught minus Tmi. So if we take a look at this expression, so mass flow rate is provided, Cp of air is a known quantity, Tm naught is the unknown. This is what we have to find out. Tmi is provided as 27 degrees Celsius, and Q is also provided, I believe. Yes, so heat flux is 600 watts per square meter, so we can always find out Q. So we can use this expression to find out the value of Tm at the exit of the duct. But in order to find out, it is a very simple equation, but in order to find out Tm at exit, all we need to know is have the value of the Cp, for which we need to assume, again we need to assume the value of Tm naught. Now it is coming in at 27 degrees Celsius, right? And so now we need to assume a particular value. You should not assume less than 27 degrees Celsius. At least we should try. See, air is flowing through this particular duct, which is 1 meter long. So at least I would suggest that we should consider. In fact, the thing is that we should also take a look at the value of the Cp while we are assuming the value. So Cp is 1, right? So Cp is 1. It means that Cp is, what is Cp? Cp is in fact the amount of energy required to change the temperature by a unit degree Celsius. So if the air is being heated up, of course it is being heated up, so therefore Tm naught would be greater than Tmi. Now we should assume a value greater than 27. Now if we take a look at the value of Q, so the heat flux is 600 watts per square meter. So if we multiply it by area, so area would be perimeter times length, right? It would be perimeter times length, right? So now this perimeter, why we have taken this area of perimeter times length, because if you visualize, perimeter would be the length of the four sides which make the cross section of that circular duct times the length of the duct. So that would be the area through which the constant heat flux will be imposed upon the tube, or that would be the area using which the constant heat flux will be imposed on air through the tube. So perimeter would be perimeter of a rectangular cross section would be the sum of its four sides that make up its cross section. So we are given that it is 4 millimeter by 16 millimeter. So it would be 4 millimeter plus 16 millimeter plus 4 millimeter plus 16 millimeter times the length of the duct, which is 1. So we get the Q as 24 watts. we do not need to calculate hydraulic diameter right now, but hydraulic diameter would be required in the calculation of the Reynolds number. And secondly, why are we interested in calculating hydraulic diameter? Because it is no more a circular duct. So we need to calculate the equivalent hydraulic diameter of this rectangular duct. So for the timing, when Q is 24 watts, Q is 24 watts. So I was saying that so many joules per second would be given to the air. Now it has a CP of 1. So 24 watts means 24 joules per second would be given all along 1 meter length. So we should at least start assuming like in excess of 70 or 80 degrees Celsius. So therefore, if I assumed that it as 100, you could have assumed it as 80 or 120 or any other particular value. So if we we were trying to calculate the mean temperature so that we could determine the value of Cp. Now if you assume that outlet temperature at 100 degrees Celsius, just for the sake of the calculation of Cp, so we would be able to get the Cp at the mean temperature, where mean temperature would be the mean of Tmi and Tm naught. So we would be able to get the value of Cp as 1.00846 kilojoules per kg per Kelvin, and then using that equation we would be able to calculate the value of Tm naught, and it will come out to be 146 degrees Celsius. Right? Now, in order to calculate Ts naught or Tw naught, the surface temperature at the pipe outlet, at the pipe exit, so we would be using H times delta T, HA delta T, where Ts naught is the only unknown in this expression besides H. So again the problem is the same, that we know the value of the heat flux, and we know the value of the Tm naught as 146 degrees Celsius. So we need to find out the value of H so that we can find out the value of the surface temperature of the pipe at pipe exit. So in order to find out H, again we have to go through the same procedure. Means we need to find out the type of the flow, whether it is laminar or turbulent, and we also need to find out whether it is fully developed or not. Kindly note that if this had been the case of constant surface temperature, then we would not have written it in this form. Rather, we had written it in the form of log mean temperature difference. This expression of Q would have then been written as H times A times delta T at exit minus delta T at inlet over log of delta T at exit upon log of delta T at inlet. Right? Now, so in order to find out the Reynolds number so that we can determine whether the flow is laminar or turbulent, so these are the parameters that we require in the calculation of the Reynolds number. We need hydraulic diameter, we need viscosity, and we need the value of U infinity, or rather um. It would be um. So if we use the continuity equation, we would be able to get the value of the velocity as 3.005 meters per second, and hydraulic diameter would be calculated in this form: 4 times cross sectional area over perimeter, wedded perimeter. So cross sectional area of this duct would be 4 millimeters by 16 millimeters, and perimeter is A plus B plus A plus B. Right? So we get hydraulic diameter as 6.4 millimeters. So putting the value of the hydraulic diameter and the velocity over here, we get the Reynolds number as 983. So since this 983 is less than 2300, the flow would be considered as laminar through the pipe. Now the last thing that we need to find out is whether it is fully developed or not, for which we need to find out the entrance length, the hydrodynamic entrance length and the thermal entry length. So since it is laminar, we would be using this expression to find out the the thermal hydrodynamic entry length, and this is the expression that we will be using to find out the thermal entry length. Again, those expressions are the same as we had used in the previous problem. So we get the hydrodynamic entry length as 0.315 meters and the thermal as 0.221 meters, whereas the length of the duct is 1 meter. So both are less than 1 meters. So it means that at the exit of the rectangular duct, the flow would be fully developed both hydrodynamically and thermally. So therefore, now we need to refer to that particular table. If you recall, since so now those values will not be 4.3 and 3.66, rather since it is not circular, we need to refer to this last slide which we were discussing, this slide. So this is the table which we will use to find out the value of the Nusselt number, and our case is that of the uniform heat flux. All we need to do is find out A by B. So now in this case A by B would be calculated, and it is 4 millimeters on one side and 1 millimeters on one side. So this would be the corresponding case, right? So B by A would be 4 millimeter by 1 millimeter means 4. So then therefore the Nusselt number would be taken as 5.33, right? So now going back to that slide, so we have found out this Nusselt number as 5.33, and then we will equate to H times D times O over K, where again dia would be the hydraulic diameter and K would be found out using the same table of properties. So we will get H as 24.1 watts per meter square Kelvin. Right, so after we find out H as 24.1 watts per meter square Kelvin, we will put that value in here, and we will get the value of Ts naught as 170 degrees Celsius. So this is how we would be able to get the value of the temperature of the surface at exit. Over here it says that after finding out, of course, after finding out Tm naught as 146, we need to correct the temperature, the mean temperature. The mean temperature would now be the average of 146 and 27, and the properties would be evaluated at that corrected mean temperature. So this is how we would be solving this problem.